Thanks for being there. So, what is finite elements? It's the thing when you have your CAD file and you want to see the mechanical deflection of whatever CAD thing you design, or a motor you just design. You want to see the torque that is created by this motor, or a pipe where you want to see the water throughput in it. You want to simulate this with finite elements. And this is basically, if you have access to a library, you could just connect it to whatever CAD software. It would compute the physics and output data that you could again show in the CAD environment. And so it would solve physics problem and predict what's going to happen, like motor torque, for example. And this is exactly what Sparselizard does. So some history, it's quite a young finite element library in terms of usual finite elements library are like 20, 30 years old. Commercial software. ANSYS is probably 40 or more years old. And so they have a lot of history, and it's good or bad, depends. But Sparselizard is quite young, which doesn't make it not robust or not mature. So it all started at University of Liège, not so far from here. During my PhD, I wrote a MATLAB finite element code, which had already a lot of all the features that Sparselizard now has. And this was like, you can see it as a draft. And from this, on 2017, I rewrote everything from scratch in C++. And so everything is really nicely integrated together. It's not something that was doing just a few things, and then it was patched and hacked around to add things more and more over time. It's really a lot of features that are there from the very beginning, and which make it actually quite nice and monolithic, and where there is no need to hack code around. And then from 2018 to 2019, I worked at IMEC, a Nanoelectronics Research Center. Some colleagues are here, and I used it. Basically, I used the software to design micro electromechanical systems, quite a wide range of them, and they were fabricated, so there's actually some industrial background in the way it was written, because it was written on the side of this work. And then for the coming 4 years, there's a grant thanks to the Academy of Finland, and thanks for Academy of Finland to bringing me here. It will be developed for 4 years at Tampere University with a slight different focus on particle accelerator magnet design in collaboration with CERN. So 4 years of basically full-time development, already paid and guaranteed. So there are lots of finite element softwares, and you could think of why there would be another one to add. Well, from my point of view, there are lots of things that just are specific to every software, and everything, well, I didn't find what I expected in finite element softwares, because they're always missing something, and they tend to be usually not easy to use. Now, here we provide a very large set of proven capabilities of a lot of different physics, which you can very easily combine, because this is the purpose of it from the very beginning, to work with highly multiphysics simulations. You have also a lot of extra finite elements, things like mortar finite elements, which works very nicely for electric motors. And all that is very concise and user-friendly. We'll see that, even though that it's a C++ library. We'll see that again later. And it's carefully validated and debugged. I spent a lot of time on validating, and so far as I know, there is no bug that I'm aware of that is still there. If you want to find some, I will. It doesn't mean there are no bugs, but if I know of a bug, I will remove it. It's also clearly documented and quite efficient. You can run it on 32 cores and get a nice speed up, and it's very rapidly expanding. All the examples that I will show, half of them have been added last year. So let's first start about what it's able to do. So this is half of the examples. So you have fluids, magnetics, electricity, mechanics, rotating machines, acoustics, thermal, simulation. They all have a demonstrated example online, and I'm not hiding anything. You can just click on this button and you will see the example, and it will always fit in 10, 20, or at most 50 lines of code, which are actually extremely readable. You can simulate Well, you see highly multiphysics things like the thermoacoustic simulation in a deformable cavity. This includes pressure, thermal, mechanics, and well, acoustics. All that combined in one simulation, or the fluid-coupled piezo-actuated MEMS. This was actually fabricated at IMEC, and this includes pressure, piezo, and mechanics. All this combined very nicely. So all these examples are validated, and there are some more. You have additional features like on the top left where you can work with non-matching meshes just very easily. And what you can simulate is, of course, transient simulations, harmonic simulations, eigenmodes, but also something specific to Sparselizard. You can simulate harmonic, in harmonic domain, things that are nonlinear, which commercial softwares cannot do at all, as far as I know. So if you have a nonlinear problem, you want to know how all the harmonics will appear. This is very, very straightforward in Sparselizard because it was really at the core of the initial MATLAB FEM code that I started with. There are lots of predefined physics as well. For example, on the bottom right, advection diffusion is very well known that if you have advection-dominated advection diffusion problems, you start having instabilities. And for that, there are 5 different schemes of stabilization that are predefined and checked that you can readily use in just one line. Now, advanced things that are available. So as I said, there is native support of the so-called harmonic balance finite element, which allows to do nonlinear harmonic analysis. There is also a fast 3D, very general unstructured mesh-to-mesh interpolation algorithm. It scales very nicely, linearly to up to 100 millionths of elements. You have general 3D mortar finite elements. So on the previous slides, here you have an example of an electric motor. In the rotor and stator, you really want to link them with mortar. This is how it's done commercially, because otherwise you don't have the freedom to choose the mesh at the interface. You have some constraints. Here you're totally free to do it. It works in 3D, no limitation. You have, well, basically I started writing this a month ago, and it will be available next week through p-adaptivity. So you can change the interpolation order on every element in the mesh, which means only on the elements that actually require to have more computation done will you perform more computation. So as an example, I have a short video that's not going to show there. So you have the electric motor simulation, and so you have the induction field, magnetic induction field on the left, and then on the right you have the interpolation order that is the best to actually solve this as accurately as possible with as few degrees of freedom as possible. And you see red, the red is the place where you have the highest interpolation order, which is 4 here. And this corresponds to the flux concentrations, which actually need to be accurately solved for. And so as you rotate the rotor, it will automatically adapt. This is just 2 lines of code to change. There is really nothing difficult to that. Well, probably in other softwares, you might get in trouble if you actually want to use it. Now, you also have extra things that you expect to have in finite element codes. Maybe a file format, which in this case happens to be compared to VTK paraview format. If you run a fluid flow simulation in time, you need to store 500 time steps. You might need 300 gigabytes of data. Here you will just need 30 gigabytes of data. It's like 10 times more compact than VTK, for example. And I don't believe it's possible to make it more compact because it just stores raw data. And you can just easily reload it. And that's the nice thing about it. It's not just dumping data and loading again. You can easily reload it later, even if you have no idea of how the simulation was done. You have one-liner probes, so if you want to know the value in one specific position, you have the interpolate function. You have maxes, averages, integrals, whatever. This is very straightforward to use. You have paraview output format, because paraview to me is the best way to visualize simulation data. And then you have Gmesh and Nastran mesh input format and lots of more input formats via PETSI that allows to load other mesh format and Gmesh as well, which you probably know a lot. You can also have curved meshes. So quite a lot of extra features, and it's growing. So probably you will see so mesh refinement coming in the next month, because this is currently what I need for the superconducting magnet simulations. Now, it's concise and user-friendly. You don't need advanced knowledge of C++. It is C++, so you can easily link it. But all the pointers and stuff are hidden. You don't have to work with the memory. There's no hack. It's highly readable. So as an example, you don't need to know the equations, but if you want to run a 3D electrostatic simulation, this is what you would need. This is a working example. 9 lines of code, 2/3 of it, which is just commands. Hard to beat, I think. It's object-oriented programming. Yeah, just have a look at the examples online. Basically, they might be just 3 times longer, but with 20 lines of code, you can run a full 3D fluid flow simulation, for example. Now, it's documented, and not just like automatically documented. It's really, I spent a lot of time to document it. So every function you're supposed to use comes with as detailed description as possible, and also a working example like this one, where you can just copy paste it and then play around with the function to see what it actually does and what the specific things are about it. This is valid for every function, and whenever I add a function, I add it immediately to the documentation. And it's available on GitHub for free. It's GPL, open source, of course. And if there's anyone who develops a CAD engine, I would be definitely happy to have some interaction to include it. Thanks.
Questions? Please.
Can you also opt to do FEM on 2D or 1D differential equations?
Can you repeat the question?
Can I do finite elements on 2D or 1D equations? Yeah, so 3D, 2D axisymmetric, 2D and 1D. Yeah. Yeah.
Please.
So the thing, maybe you just explained it and I missed it, but doing thermal analysis, it's quite easy to get point outputs from some of these tools.
Yeah.
But what you actually want is like an area summation.
An integral.
Do that easily?
An integral. Oh, you want to have like an average value for a thermal problem? You want to know the average temperature or something?
If you're trying to measure heat flow,
Yeah.
you get point heat flow because that's sometimes unstable. You want to say,
I agree.
Square meter.
So if you want to integrate the heat flow through a surface,
Yeah.
it's one line. So you have access to the normal, you multiply by the heat flow, you dot integrate, you see on which region, what integration order, and you're done. You have a double value out.
So, go ahead.
Do you support any shape optimization or topology optimization?
So topology, I don't myself, but I support topology optimization? I don't myself, but a former colleague managed to do mechanical topology optimization. There is an example online, but no example button to click on because it's his software. But yeah, you definitely can because he did a 2D bridge topology optimization in mechanics.
So it's possible to get sensitivity information.
Yeah, he did it, so I can confirm it's possible.
In the very back.
So for thermal modeling, can you only model conductive heat or can you do combined conduction and radiation?
I can.
Can you repeat?
So if for what I heard, am I limited to like conduction and can I do other things of thermal analysis like other problems like convection, radiation, and heat? There's an example online for conduction. You can also have. There's also an example for natural convection. So that works as well quite easily, especially now with the stabilization methods added. And radiation, I haven't tried it. So of course, you can probably find out the equations that correspond to how much you lose, but you cannot take into account the fact that you radiate on another phase for the moment, although maybe particle tracing is being added, maybe it can somehow do that, but radiation would be the only thing that's missing.
So, yeah. Go ahead. Yes. Speak up.
Okay, how is the turbulence treated in your model? Because in some cases I've seen in the website that you are using, for example, in fluid structure interaction, because in some of your cases the type of turbulence closure models plays an important role.
So you're interested in including turbulence in the simulation for the thermal convection.
No, just for
General fluid. So actually that's funny because one month ago I thought, what am I gonna do next? And I thought I'm gonna add a turbulence model for a fluid flow model with a Sparselizard Almaraz, and everything is ready to add it. It's just that I thought it's too specific. I don't want to write something that is just for incompressible fluid in this specific case. I think for the moment the user will have to write it in himself. But Sparselizard Almaraz at least is easy to add, and the only thing you need in this case is to know the distance to the wall. And this, if you need help for that, I know how to do.
Yes, right in back.
How difficult is it to change or creating new type of element with a different set of shape functions?
If you want to add a different set of shape functions yourself, I think it's quite easy. So you have like a folder with all the H girl shape functions, all the H1 shape functions. You could just create another one, and it also this all is quite readable because it's called a polynomial function where you can just make products of polynomials which you first define, and based on what is already there, I think it's really doable for a user. It's generated. What I didn't fully understand is my stiffness matrix explicitly or build up. With the way it's built, I call a function that creates a math object which includes all the terms of the stiffness matrix, and this is created in basically the core of Sparselizard, a function that calls everything that needs to be called and just assembles very efficiently all the terms in the stiffness equation. What? Yeah, you can. I tried with up to 50 million degrees of freedom in 2D, and 5 million degrees of freedom for fluid flow in 3D. Of course, on bigger machines, but not like supercomputers, but more 32-core machine with 700 gigabytes of RAM. And yeah, definitely this is doable. The only limit for now is that I call PETC to call mumps, because mumps is efficient in solving algebraic problem. And for now, PETC doesn't call the new version of mumps, and so it's limited to a number of non-zeros in the matrix that is less than about 1 or 2 billion, which limits 2D problems to 50 million unknowns. But so what refinement this is not in the documentation. That it will be released on Wednesday, but it will be up to the user to choose. So, for example, you can, because that gives you the most flexible thing. For example, you'll be able to, in the motor example, you have a vector potential, and then you could just say that you check on the norm of the gradient of the z component of the vector potential, basically to see where things are sharper, and where it's sharper, you have like corners and stuff, and there that's where you want to refine more. So, but it's up to you to choose with whatever expression, because you can build any expression easily in Sparselizard to choose it.
All right, thank you.